tonight we're looking at Newton's method. Newton's method is a way to approximate the roots of a function. So roots, remember, that's just where the function is equal to 0. So this is a numerical technique. Specifically, this is an iterative technique, so it requires iterations. The general idea deals with tangent lines. So I'm not going to go through the entire derivation. But you make an initial guess, right, and then you use that guess to find a value. You're going to then use that value to calculate your next value, so on and so forth. And the idea is you're going to, if you picked it right, converge to your actual root. And this is deriving it with your initial guess, right? So you use tangent line. Right, then x1 would have to satisfy that equation equaling 0. Solve for x1. That's what you get. Right, well, now you want to find an x2 based on that x1, and the process is pretty much identical. You're going to find it's x1 minus f of x1 over f prime of x1. So in general, x sub n, x sub n minus 1 minus f of x sub n minus 1 over f prime of x sub n minus 1. This is your iterations. That is the actual iterative process itself. Again, generally what you want to do is you want to repeat the iteration until you reach some desired accuracy. Right? Usually 10 to the minus 6 is the accuracy, 6 decimal places. I've gone as far as 10 to the minus 9 decimal places. Here's where it gets fun. You don't know how many steps you need to reach that accuracy. You can actually calculate it using error analysis, which I'm not doing in this course. But generally speaking, the number of steps is fairly large. I've seen some where it will require more than 10 to the 9th iterative steps to get your accuracy. You want to do that by hand, be my guest. I won't stop you. This is where coding is going to come in. So we will be doing some hand calculations as well as some coding. I mentioned that's an iterative process, so I won't get too much more into that. Now, there are some weaknesses with Newton's method. One of the issues is if you get a point where the derivative is 0, well, now the whole thing just fails because you'd be dividing by 0. That's a problem. If you pick your initial guess poorly, it may go to the wrong root. they go to a root that you're not looking for. So you kind of need to have an idea of what the root is to make a good guess to begin with, so that is an issue. Again, depending on your x naught, they could also just diverge. So the process may just straight up diverge, which means unless you put in a fail-safe, the code will just run indefinitely. We will be including fail-safes as well. Actually, you don't have to worry about it if you're using Wolfram Online. The free version has a built-in timer. I think it's 60 seconds before it just stops. If you are using the paid version, though, I don't think there is a upper limit on the time. So you have to build in a fail-safe. Right, that just kind of shows you could go to the wrong route. X cubed minus 2, compute the first 3 iterations with an initial guess of 1. And it's not giving us a specific number of decimals. I'm going to use 7. The function that we're looking at is x cubed minus 2. What is that prime?
3x squared.
And of course, our initial guess is 1. There's the first iteration, x1. X naught minus f of x naught over f prime of x naught.
What about you? Value.
So we're going to do this on a calculator. And I'll show you probably the easiest way to do it. So first, define your function. I'm also going to define its derivative. This derivative isn't hard, but I'm going to show you how to calculate the derivative. And so menu calculus derivative. With respect to what? X. And what are we taking the derivative of? F of x. And now that's stored. I'm not going to hit my initial guess. It was 1, right? I'm going to put a decimal after this. That decimal is going to approximate all values for me. So it's x naught minus f of x naught divided by, no, not true. Divided by f prime of x naught. Then just hit enter. There's x1. So there's a reason why I went through that whole process ahead of time. Hit enter again. There's x2. Hit enter again. There's x3. This way I'm not constantly retyping it in. So x1 is just 1.3 repeating. X2 was the 1.2638 repeating, and x3 1.253493495. Oh, is that? No, it's not. Oh, bummer. I'm sure there's a repeating pattern in there somewhere. Two, and finally x. Two, 5. Yep. 3, 3, 5. There's the first 3 iterations from this method. Now this is good for a warm-up, right? This is good to actually see how the method works, because we know what the exact root is. What is the root of x cubed minus 2? Cube root 2. You can approximate cube root 2 and show that these values, if you keep going, are actually converging to that. So Newton's method does work. Cosine of x equaling x. We want to solve that. Would that be possible to actually solve that? Don't think so. So I don't think that can analytically be solved. I think you're going to have to use a numerical technique. Obviously, we only know one Newton's method. So that's the one that we're going to use. And they tell us to guess. Initial guess of 0.5. And then it wants to go up to x3 again, so because we're doing it by hand just the first few iterations. I'm going to assume 7 decimal places all the way through. You need your function. Well, remember what Newton's method is doing. It's approximating the root of f of x. That means it's solving f of x equals 0. So if cosine of x equals x, what's the function?
Cosine over x.
That equals 1.
Oh,
Or x minus cosine x, either one would work, right? What's its derivative?
Minus sin x minus 1.
And an initial guess of 0.5. Now it's calculator work. Just gonna copy paste. Just change this to sine of x, I'm sorry, cosine of x minus x. And so redefine my two functions. Put in the initial guess of 0.5. Right now, we're off to the races. Again, I'm lazy. Except I'm not going to do, isn't that annoying? That's a bummer. I am unfortunately have to re-enter. Oh, you can't actually see my pen cursor. That's nice. There's x1. It's in my notes. I'm sure that's wrong. There's x2. And there's x3. from this, it appears to be approaching, it does appear to at least be approaching something, right? So it does appear to be converging. Unfortunately, I can't determine what it's converging to.
It's the value where cosine of x is the arc cosine. I think. But I don't know the value, so it doesn't matter.
Right, yeah, whatever that happens to be. Right, we can't determine that from here because the values are still too far off. If I do another iteration, I could probably determine it. That's okay, it's not asking us for that. It's just asking us to find x1, x2, and x3. Oh, okay, cool. This is not on my example sheet. That one is. Oh, wait, no, that's that one. Okay. So there's our function. First, we're going to plot it. Then consider the two different starting points, negative 1.6 and negative 2, and use Newton's method to determine what those iterations are going to converge to. For each starting value. So here, I think we will now go into different. This one's not going to require the actual loop coding just yet. Six. I think that's supposed to. Yeah, that's a typo. Wrong value. That should be. here.
R2.
I'm going to plot f of x for what values? Let's go -2, too. Okay, let's go -3, 3. So it looks like the roots, and again, this is a polynomial, so we can easily find it. -2 and +1. So -1.6 is going to be, what, maybe right about here. We hope that that's going to converge to -2, right? 1.8 is right there, and we hope that that's going to converge to 1. But let's actually take a look. So here's what I'm going to define my two starting values. I'm going to say A is -1.6, B is 1.8. Oh, shit. Maybe I will need to do the while loop. No. Let's define nm of x. We define this to be my iterative process itself. X minus f of x divided by f prime of x, right? That's stored in. Yes. So x1 would be nm of a, right? -2.07273. nm percent, that percent is the last output. Oh, okay, well that's pretty conclusive. It is converging to -2, which is what we wanted, right? Yay. Now using 1.8 as an initial guess. There's x1. X2. X3. It's looking good, right? X4 and that converges to 1. Oh, good. So Newton's method is behaving the way you would expect it to behave. Solve e to the x minus 3x equals 0 with an accuracy of 10 to the -6. And they're telling us to use 1 as our initial guess. find the function first. It was e to the x minus 3x. We define a term called accuracy. Which is my 10 to the minus 6. I'm also going to introduce a variable called error. I'll start that at 1. Pick an x naught. We said that's going to be what, 1? And I'm going to put a decimal, again, because I want approximations. N is my index, right? Start that at 1. Because xn equals something for n greater than 1. So my index starts at 1. I think I should have everything I need now. That's the quote-unquote preamble. Right? That's setting all my variables. Now for the actual body. I'm going to use a time constraint because I don't want it to run indefinitely. Again, for the free account, you don't have to worry about it. It has a built-in time constraint of, I believe it's 60 seconds. I'm going to use a while loop. For a while loop, you need to first identify the test. I want it to run as long as the error is larger than the accuracy. In addition, I'm going to set an additional stipulation and say if it equals the accuracy, I want to at least go one more. Comma. So that's the test. So it runs that test. If it comes out true, it's now going to do what I tell it to do. If that comes out as false, it kicks out of the loop. What we're going to have it do is calculate xn. So I have to type in the formula. Right? Semicolon. So I want it to do multiple things. So first it's going to calculate my next step in the iteration. I then want to recalculate error. Absolute value. Of what it just calculated minus the previous. Or if you do previous minus what it just calculated, doesn't matter. Because you're doing absolute value, it's the same thing. Then I wanted to add 1 to the index. N++ is shorthand for that. That is the end of the while loop. So what it does, checks the error, compares it to the accuracy. If the error is larger, it'll calculate our next iteration, recalculate error, add 1 to the index, then go back up to the test. If that test is still true, it'll go back into the body. And it's going to keep doing this until the error is less than our accuracy. which is what we want. It'll then kick out. Now to deal with the time constraint. Because I have no idea how long this process is going to run, and I don't want it to run forever. Again, I think 60 seconds is the time limit for free. So let's do 50 seconds. And it is in seconds. Right? So if you want 5 minutes, it's 300 seconds. If it goes beyond that time, I'm going to have it just print something saying that the time has been exceeded. Right? Something to signify that we went over our time constraint. I don't know. Time constraint has been exceeded. And the time constraint. Right, so there is the entire loop with the time constraint built in. But notice that in the actual while thing, I don't have it printing anything. It's just storing all these values. Well, now I want to actually print something out. The root, initial guess. All right, so again, remember anything in quotations, it's going to read it as just text. So print that out directly. With initial guess of x0. Is so I want to print out what it gave, what it calculated, the last thing it calculated. But remember, before kicking out of the loop, it did what? Added 1 to the index. So I don't want n. I want n minus 1. So it added 1 to the index already. So let's say it took 5 steps. N would be 6. I want x5. Period. And just because I'm curious, this process I'm also going to have it tell me how many iterations it used. There's the entire thing. Now, just execute it, shift enter. Oh, look at that. Took no time at all. And it gave me 6 decimal places, which is nice. So you get about 0.619061. And what I'll do is I'll just copy that. And put that on there. I won't show any of the code. Because that would be too much. In fact, I'm debating whether I'm going to upload this file or not. I don't think I will, because your third project is news method. Why would I give you the code? Why would I just give it to you for free? Solve natural log of x plus x equals 3 with an accuracy of 10 to the minus 6 and an initial guess of 2. Now, normally, I would just come up here and just adjust some things. Oh, you've got to be kidding me. Are you seriously not going to scroll? You can read that, right? What's f of x?
All x plus x minus 3.
What is the accuracy?
0, 10 to the minus 6.
And so if I come back here, accuracy is not going to change, right? Function will. Error is not going to change. In fact, probably as a general thumb, always start with 1 as your error. You can go even larger if you want to. What is x0 going to be?
2,
And what is n going to be?
2. Oh. It's still be 1.
Yep. Again, you always want to start at 1, right? Because you want to calculate the first iteration first. So there's only 2 things changing. F of x and x0. Log of x plus x minus 3. In Wolfram, log is by default base e. If it's a base other than that, I think it's this. I think that would signify log base 10 of x. I think the base goes first. And again, I want to keep that decimal there because I want it to approximate. And I don't have to change anything else. The code's going to be exactly the same. I can now just execute this. This only took 3 iterations to converge. There is a problem though. It only gave 5 decimals. It did not give me 6. Because it gave me 6 significant figures. I have to fix that. There's 2 ways, I think. form also works. Yes, okay, perfect. I'm actually going to use number form, I think. All I have to do is change it here. I'm going to do it in, just go 100, and I want 6 decimal places. So that first one's saying how many precise digits do I want to calculate to? The second is how many digits to the right of the decimal place do I want? Because generally speaking, you're not going to know how many digits it's actually going to be until you run it. Just pick a really large number, 100. I highly doubt we're going to get 100 digits. Now just execute, boom. There it is. Again, except that is not what this has. What was it before? Yeah, okay, same thing. Did I type that in right? That's wrong. Anyway, just do this. In fact, I think I could also do this. Infinity 6. No, it doesn't like that error. Oh, okay, it doesn't like that. So I'll just pick a really large number. Huh? Oh, somehow that changed. That changed. Good. Okay. That'll work. Now, if I actually solve, if I use the solve command, I wonder what's going to be. And solve. And so again, I'll just do this. You can also use Newton's method to approximate values of irrational numbers. Right, so Newton's method to approximate the value of root 2, accurate to 6 decimal places. Now remember what Newton's method is doing. It's finding roots of a function, right? So if I want to approximate the value of square root of 2, which is called an algebraic number, by the way, what function are we going to use?
Root x.
So ask yourself, what function has root as square root of 2?
Would it be root x minus root 2?
You got 1, right?
X squared minus 2.
X squared minus 2 is one such function. It's probably the best one to use. So that is our function. So we'll do real quick. We said x squared minus 2. We want 6 decimal places, right? Accuracy of 10 to the minus 6. Leave the error. What do you want your initial guess to be?
One.
Start with 1. And I can leave everything else. There's root 2 to 6 decimal places. How many iterations did it take?
1.
So what would happen if instead I said 1.5? Do you think it would be faster or slower?
That's closer.
Only by 1 iteration. Closer doesn't necessarily mean faster. I could get it close and then have it completely diverge. Right, but you want to be in the ballpark. That's Newton's method. I'll do is do this. Probably also just do this.
Is this not computers approximate roots?
I highly doubt they use Newton's method. It's too inefficient. It does use a numerical technique, but it's going to use a way more efficient one.
Okay.
And again, I'll just put that. Do that. Question on Newton's method. So don't forget the second test is due Thursday. And so the second test is just derivatives. The Newton's method homework due next Tuesday. There are a mixture of problems on there, I believe. So it's going to have ones like what we did, calculate the first 3 or 4 steps. And I think it's also going to have ones that are going to ask you to find the root to a desired accuracy. The third project, giving you 2 weeks to work on it. And so it's due the Tuesday after next. It's just on Newton's method. So you're going to have to write code using a while loop. So like what we did in class. Now here's the good news though. I forget how many problems it is, but you only really have to write the code once, right? Because then you can just copy and paste it, and then just make the minor changes that you need. So let's actually take a look at the assignment details. Let's see what it's asking us to do. Why is it being weird? Oh, okay, there we go. So it wants you to do a 30-second constraint. I don't want you sitting there letting it run for too long. And so again, if it's going to exceed the time limit, just include some kind of output signifying that the time limit's been exceeded. even if the time limit's exceeded it, you can still print out an answer. Like, it still keeps storing all those values until the time limit has been reached. So you can still print out the last thing it gave you. I'm not asking for a PDF. Because I want the actual code as well, so I can try to execute it. So the entire write-up will be done within the Wolfram Notebook file itself. Again, using your text cells. If you're using the Wolfram Cloud, you will have to download the file to attach it. I have the desktop version, so I will be able to open it, so don't worry about that. Just attach the notebook. And there's going to be 6 questions again to do.
Does Wolfram allow you to make collaborative files?
It should,
Okay.
but I know that someone was having a problem with that. So I think what wound up happening was because it is a cloud, right? So you can share the cloud file. The problem is I think it only allows one person to work on that at a time. So if someone has it open, weird things are going to happen if someone else tries to open it. And I also realized that with the free version, it doesn't allow you to upload files. So I would recommend figure out the person who's going to be doing the Wolfram, have that person keep the file. And then just help them with the typing up. Instead of trying to have them download and send it to you, because you're not going to be able to upload it without the paid subscription. I get mine for free because they're Roman, so you can't just send me the file, that's fine. And so 6 questions. All of them want 6 decimal places, accuracy of 10 to the minus 6. And that's all this project is. Just those 6 questions using Newton's method. Wait a minute. Why is that on there? We literally just did that one. But I think it's using a different starting point as well as 3. So, whatever, that's fine. I don't care. Six is of particular interest to me. Because that's the golden ratio, which if you remember is my favorite number. So I need shorter. This shouldn't necessarily be that difficult of a project to do. The hardest part's going to be actually writing the code for the first time. After that, it should be a piece of cake. So I would recommend you get started on it, so that if you run into any problems with the code, we can go over it before it's too late. The 4th project I have decided will, again, be another coding. It'll have to do with approximating areas when we start studying the integral. So that'll be the 4th project, approximating areas to a desired accuracy, which is going to be another while loop, pretty sure. That one, though, you're not going to have the advantage of me doing it in class, I don't think. Ahead of time, that's going to be one you're probably going to have to do it from scratch. Just a heads up. For the worksheet, you don't need to do any kind of code. It's all just calculate the first 3 iterations, and then there is a thought exercise as well. So you won't need to do any coding on this.
Do you have the worksheet from the class that we had missed?
I did send it through Teams though.
So it'll be like on Blackboard?
It's a Teams message. So if you open up Microsoft Teams, you'll see that I sent a message with attached files. It's there. You can just download it from there.
All right.